Welcome to the deep dive. Today, we're tackling something big. The whole blueprint for data science and data engineering. It's a massive field, right?
Absolutely huge. But we've kind of distilled it down, following ACM recommendations, into a structured path. The idea is to give you the core knowledge you need.
Yeah, to follow a project from, the initial question right through to getting a model out there working.
Think of it like getting the schematics. We're not just looking at the cool new tools, but the essential structure, the pipeline that makes sure your results are actually solid.
Okay, so let's start with a toolkit.
Mm.
If data science had a main language, it's Python, wouldn't you say?
Oh, definitely. Python's the hub, and it runs on like a key trio of libraries you absolutely have to know.
Right, the stack. Tell us about that.
So you've got Pandas. That's your go-to for tabular data, these things called data frames. Think spreadsheets, but way more powerful.
Okay, so that's for organizing the data. What's next?
Then Scikit-learn. That's where you find most of your standard machine learning algorithms. It's kind of the workhorse for modeling.
And the third? Visualization, I guess.
Exactly. Matplotlib or Seaborn for making sense of it all visually. Charts, graphs, you name it.
And yeah, sure. There's R and visual tools like Orange or Kinian.
They exist, yeah. But Python really dominates in most business applications now.
So we have these powerful tools,
Mm-hmm.
but how do we actually use them to solve a problem? We need a roadmap, right?
Exactly. Every solid project needs a plan.
Yeah.
And the standard is CRISP-DM. That's the cross-industry standard process for data mining.
CRISP-DM. Okay.
Yeah.
It gives you structure. How many phases are there?
6 phases. It's a sequence.
Let's listen out.
Yeah.
First is business understanding.
Right. Defining what you're actually trying to achieve. What's the objective?
Then data understanding.
Yeah.
Looking at the data you have, checking its quality, that sort of thing.
Yep. Then comes data preparation. And this is the big one.
Come back to that. What's after prep?
Modeling. Choosing your algorithm. Then evaluation, seeing how well it actually performs.
And finally.
Deployment. Getting the model out into the real world, doing its job.
Okay, let's pause on phase 3, data preparation.
Mm-hmm.
You said it's the big one. We keep hearing this 80% rule. Is that really true?
It really is. It's the unglamorous reality. Most of the time, maybe 80%, is spent cleaning, formatting, basically wrestling the data into shape.
So these highly paid data scientists spend most of their time not building cool models, but fixing typos.
Pretty much. It's often called beta munging. And look, if you skimp on this phase, your fancy model is useless. Garbage in, garbage out, right?
GI go. Okay, so data prep is absolutely foundational.
It's everything. Get that wrong and nothing else matters.
All right, if you're spending 80% of our time there, let's really dig into preparation, starting with just getting the data.
Okay, acquisition. First, you distinguish between primary data, stuff you collect yourself, original source.
And secondary data.
Right, stuff someone else already processed. Think Wikipedia versus, say, an official government statistics office like ISTAT. Secondary data can be less reliable, so you need authoritative sources for core facts.
Makes sense. Now, often you get too much data. Why is reducing data size sometimes necessary? Isn't more always better?
Not always. Too much noise or irrelevant stuff can actually hurt accuracy and, well, it definitely slows things down. Calculation time can explode.
So how do you reduce it effectively?
Several ways. You can narrow the focus of your investigation, collect data less frequently, or use sampling. Simple random sampling, or maybe stratified or cluster sampling if you need more structure.
And there's also discretization, right? Turning numbers into categories.
Yeah, that's a neat one. You take something continuous, like exact age, and put it into bins, like 20s, 30s, 40s. Some models prefer that. It simplifies relationships.
Okay, shifting gears a bit. What about text data? That seems like a whole different challenge. Machines like numbers, not words.
Exactly. That's natural language processing, NLP. The core challenge is turning raw text into numerical vectors that a machine can understand.
How do you start? Just count words.
That's one way, yeah. The simplest is maybe the bag of words model. It just looks at which words are present or how often they appear, ignoring grammar completely.
But that feels limited. Doesn't it miss a lot of meaning? And what about common words like the or a?
Right, that's where TF-IDF comes in. Term frequency, inverse document frequency. It's clever. It automatically downweights words that appear everywhere because they don't help distinguish meaning.
So it filters out the noise words?
Precisely. It gives more importance to rarer, more informative terms. But even before TF-IDF, you have to clean the text itself.
Like removing those stop words and the is.
Exactly, and reducing words to their root form. stemming, or lemmatization, usually using libraries like NLTK and Python.
Okay, so that's text. Back to general data cleaning. What about ensuring consistency? Like if one customer has 3 different emails.
That's entity resolution. You need algorithms to figure out that those 3 emails, maybe with slightly different names, all belong to the same actual person, one unique entity.
Got it. And what if you have 2 reliable sources, but they disagree? Like one says a customer's age is 40, the other says 42.
Conflict resolution. You use truth discovery algorithms. Things like majority voting, or more sophisticated ones like Truth Finder, help decide which value is most likely correct.
Interesting. And then there are outliers, right? Those weird extreme values.
Absolutely. You need to spot those because they can really mess up your models. Box plots are great for this, using the interquartile range, the IQR, to flag potential outliers.
So after all that, resolving entities, finding truth, handling outliers, what's the final goal?
Data integration, bringing all your cleaned up, validated data from different sources into one unified, trustworthy view. That's the foundation you build everything else on.
Okay, the 80% is done, the data is clean, integrated. What's the very next step? We usually look at it, right? Visualization.
Yes, and it's not just about making pretty charts. Visualization is fundamental. It helps you synthesize complex info, spot patterns you'd otherwise miss.
They have a history too, doesn't it? You mentioned William Playfair.
Yeah, the pioneer. He invented the bar chart, line graph, pie chart. They're basically the tools we still use every day to communicate statistical ideas.
And Florence Nightingale. Her rose diagram wasn't just data viz, it was a political weapon almost.
Absolutely. She used it to show that poor sanitation was killing more soldiers in the Crimean War than actual battle wounds. It drove real change. Powerful stuff.
So there's a principle there. Something about ink.
Maximize the data-ink ratio. That's the idea. Use the ink on the page primarily to show the data itself, not decoration or clutter. Make the graphic essential.
And different charts tell different stories, right? You need to pick the right one. For showing how data is spread out.
You could use a box plot, sure. Shows quartiles, outliers. But a violin plot is often better. It shows the whole distribution shape, especially if it's multimodal, with multiple peaks.
And for relationships between things.
Scatter plots for 2 variables. Heat maps for correlations across many variables.
What about showing flow? Like users moving through a website.
Sankey diagram. Brilliant for that. The width of the arrows is proportional to the flow volume. Really intuitive.
All this feeds into EDA, exploratory data analysis.
Right.
What's the core idea of EDA?
It's about, well, the quote is looking at the data to see what it seems to say. It's discovery. Generating hypotheses, finding insights before you start formal modeling or testing.
Less about proving things, more about understanding what's there.
Exactly. Pure exploration.
All right, exploration done. Now we build the model, the prediction machine. What exactly is a model in this context?
It's basically a mathematical description, a set of rules or an equation that you use to make predictions or draw inferences from your data.
And when choosing one, there's this principle, Occam's razor.
Yeah, keep it simple. The simplest model that does the job, the one with the fewest assumptions, is usually the best. It's easier to understand, easier to interpret, and often more robust.
Robustness. That brings up accuracy versus robustness. How do you explain the difference quickly?
Okay, think of it like studying for a test. Accuracy is how well you do on the practice questions you've already seen, how well the model fits the training data.
And robustness.
Robustness is how well you do on the actual exam, the questions you haven't seen before. It's the model's ability to generalize and predict new, unseen data well. In the real world, robustness is what counts.
Right. So how do we measure performance for number predictions like house prices?
You'd often use something like mean squared error, MSE. It penalizes larger errors more heavily.
But for classification, like, is this email spam or not spam? Yes, no answers.
Then the confusion matrix is your starting point. It's fundamental.
Break that down for us, the matrix itself.
It's a simple table, usually 2 by 2 for binary problems, but it can be bigger. It just cross-tabulates your predictions against the actual truth. It shows you true positives, true negatives.
The correct predictions.
Right. And then the errors, false positives, which are type 1 errors.
Like calling a real email spam bad.
And false negatives, type 2 errors.
Like letting spam get into the inbox. Also bad. But maybe differently bad, depending on the situation.
Exactly. That's the crucial point. The cost of each error type is different. That's why we don't just look at overall accuracy. We derive metrics from the matrix.
Like precision and recall.
Precisely. Precision asks, of all the emails I called spam, how many actually were spam? High precision means few false positives.
Okay. And recall.
Recall or sensitivity asks, Of all the emails that really were spam, how many did my filter actually catch? High recall means few false negatives.
And there's often a trade-off between them.
Often, yes. Improving one can hurt the other. That's why we also look at the F1 score, which is a harmonic mean of both. It gives you a balanced view, especially if your classes are unbalanced, like having way more non-spam than spam.
Got it. So understanding these metrics helps choose the right type of machine learning algorithm.
Definitely. Broadly, you have three main categories. Supervised learning is when you have labeled data, you know the right answers. Used for classification and regression, think k-nearest neighbors, decision trees.
Okay, what if you don't have labels?
That's unsupervised learning, used for finding patterns in unlabeled data, clustering, like with k-means, or reducing dimensions with PCA, principal component analysis.
And the third type?
Reinforcement learning. That's different again. It's about training an agent to make sequences of decisions to maximize some long-term reward. Think game-playing AI.
Okay, let's dive into some of the more advanced stuff. You mentioned PCA for unsupervised learning. Sometimes we run into this. Cursive dimensionality. Sounds ominous. What is the Hughes phenomenon about?
It does sound dramatic, but it's a real issue. Basically, as you add more and more features or dimensions, your data points get spread further and further apart in that high-dimensional space.
So, why is that bad?
Because distance metrics start to break down. Everything starts looking equally far away from everything else. If many of those extra dimensions aren't even relevant, your classifier gets confused, performance actually degrades. Too much irrelevant information hurts.
So, more features isn't always better. We need to reduce dimensions sometimes. PCA is one way.
Yeah. PCA is the classic unsupervised method. It finds new, combined dimensions, principal components that capture the most variance in the data, letting you discard the less important ones. You often use a scree plot visually to decide how many components to keep.
What if you've already built a model and just want to know which original features were most important?
Then permuted feature importance, or PFI, is really neat.
How does PFI work?
It's clever. You take your trained model, then, for one feature, you randomly shuffle its values across all your data points, breaking any relationship it had with the outcome. Then you reevaluate the model's accuracy.
And if the accuracy drops a lot?
Then you know that feature was really important. If accuracy barely changes, the feature probably wasn't doing much. Simple idea, very powerful.
Okay, but even if we know which features are important, some models, especially deep learning ones, are like black boxes, right? Hard to understand why they make a specific prediction.
Totally. And that's a huge problem for trust and accountability. That's where explainable AI, or XAI, comes in. We need methods to pick inside the box.
Like what tools do we have?
Well, one is the partial dependence plot, or PDP. It shows you the average effect of changing one feature on the model's prediction across all the data. Gives you a general trend.
Average effect.
Well,
But what about explaining one specific prediction? Like, why was this loan application rejected?
for that level of detail, you need something like SHAP, based on Shapley values from game theory.
SHAP, how does that work?
SHAP assigns a specific contribution score to each feature for each individual prediction. So for that rejected loan, SHAP can tell you exactly how much the applicant's income, debt, age, etc. contributed, positively or negatively, to that specific reject decision. It provides instance-level explanation.
That's incredibly useful for fairness and debugging. Okay, let's quickly touch on deep learning itself. It all starts with the perceptron, right? Building artificial neural networks.
Yep, the perceptron is the basic building block. ANNs are trained using optimization algorithms, most famously backpropagation, often with variants like stochastic gradient descent.
And for sequences like text or time series, the models got more complex.
Right. Simple RNNs had issues with memory and vanishing gradients. So we got LSTMs and GRUs, which were much better at handling long sequences.
But now the state-of-the-art is transformers.
Yes, transformer neural networks, TNNs, using the self-attention mechanism. That's the core idea behind huge models like BERT and GPT that understand language so well.
And for images, different architecture.
Yeah, convolutional neural networks, or CNNs. They use these things called kernels or filters that slide across the image looking for local patterns. The clever bit is weight sharing the same filter is used everywhere, making them efficient at finding features regardless of location.
And even CNNs have advanced versions, like ResNet.
Exactly. ResNet uses skip connections to help information flow better through very deep networks, preventing gradients from vanishing during training.
Wow. Okay, so we have all these complex models. Is there any way to automate building them?
There are efforts, yeah. Automated machine learning, AutoML tools like TPOT try to automate the whole pipeline, data prep, feature selection, model choice, hyperparameter tuning.
Trying to take the human out of the loop, or at least speed things up.
Speed things up, definitely, and democratize access. Finally, once you have a great model, you need to deploy it, put it into production.
Which, for big data, means dealing with scale.
Absolutely. You often need parallel processing frameworks like Apache Spark to handle the volume and speed of real-world data streams. Deployment is a whole engineering challenge in itself. Hashtag, tag, tag, outro.
Okay, that was quite the journey. We went from the critical 80% rule for data prep all the way to needing sophisticated XAI tools like SHE to understand a deep learning model's specific output.
Yeah, we covered the whole pipeline. Understanding that structure, that flow is key. It gives you the context for how these complex projects actually succeed.
You really get a sense of the whole landscape now.
Hopefully, yes.
Okay.
You can see how all the pieces fit together.
We talked about visualization pioneers like William Playfair and Florence Nightingale, and that principle, maximize the data-ink ratio, make the data the star. So here's a thought for you listening. In your own work, with all the information flying around, emails, reports, data points, how can you apply that principle?
Yeah, how can you maximize the data ink? What can you cut out, simplify, or focus to make your message or information as clear, essential, and maybe even as impactful as Nightingale's rose diagram was?
Something to think about. Thanks for joining us on the Deep Dive.